Hello everyone, today I've explained the architecture fast RCN, which could also be used to solve object detection problem. And according to the paper, fast RCN is faster and more accurate than RCN and SPPNet. We know that fast RCN is created based on RCN and SPPNet. So first, I will explain the SPPNet, and then I will detail the RCN. Okay, we will explain the SPPNet. We know that this is RCN, and for RCN, this is the region proposal. And for a region proposal, since we use AlexNet and the input size is fixed, so we have used method to change the input size. For example, here we use this method to change the input size. And then we train the model like this. For SPPNet, the authors ask a question, why we have to change the size? And if we change the size, it also causes unwanted geometrical distortion problem. So the SPPNet proposed a new method which avoid this problem. So for SPPNet, which means we don't need to change the input size. So he resolved the problem like this. We know that for the last part, this here, for the convolutional 5, here we use a max pooling. And for max pooling is like this. For the input size is 13 by 13, and then the number of channels are 256. So he used a max pooling size 3 by 3 and stride to get 6 by 6. And the channel is also 256, and then we get a vector like this to represent the input. And this is for RCN. And for SPPNet, he used a method, so which means whatever the input size, he will get an output size like this. So the method is like this. He used, for example, max pooling to first get a matrix 4 by 4, and then by the number of channels, and then use a second max pooling to get the output 2 by 2, and then use a third max pooling method to get 1 by 1, and the number of channels are the same. So the size of the max pooling could be changed. For example, if the input size is 13, and since we get 4 by 4 by 256, so we use this 13 divided 4, and then we use round up to get 4, and then 13 divided 4 we use round down, so we get 3. So the second part is 13 divided 2, and then we get 7, and then 13 by divided 2 we get a round up, so we get 6. So with this method, so whatever the input size, for example, if we have 15, it's also like this. For example, 15 divided, and then we use this method, we could calculate it. If the input is 15, we also get the result like this. So for SPPNet, he used this method to, for example, to get a result. Whatever the input, we have the same result. This is SPPNet, the important part of the SPPNet. So here is the detail of the SPPNet. For example, this is the same. For SPPNet, he also used AlexNet like this, but for this part, overlapping or max pooling part, he used this one. For example, he used this part changed by this part. For example, 4 by 4, 2 by 2, 1 by 1, and then we get a result, and then we concatenate the result here like this. So this is SPVNet. So for fast RCN, he also used this idea to create a max pooling like this. So we will detail that in the following part. For fast RCN architecture, this is fast RCN architecture. You can, so it's like this. We know that for RCN, the input is each region proposal. So if we use this, for example, if for RCN we use this region proposal as input, for example, this one and this one and this one. So we have 2000 region proposal and and then we have to compute 2000 feature map for each region proposal. This takes a lot of time. But for fast RCN, the input is one image, it's not the region proposal. So for one image for fast RCN, we compute 2000 times, but for fast RCN, we just only use one time, compute one time for image. But how can we get for example, the feature map which could be used to represent the region proposal? Here we use ROI projection, which means we project the box into this one, and then after we get the project coordinate, we get the feature map like this. So for each region proposal, we project the coordinate, we get this one and use this one to represent each region proposal. So here after the region proposal, after this part, we use ROI pooling layers. For this one, it's just like SPVNet. SPVNet, we know that there are three matrices which represent, with these three max pooling, we get 4x4 and 2x2 and 1x1. 2x2, 1x1. But for this part for fast RCN, we just get the result 7x7 with one time, and the idea is just like the same. For example, we don't need this one, and instead of 4x4, we use 7x7. So it's like this. And for the result, here we have two outputs. One is for softmax, and the other is for bounding box regression. With softmax, we would like to do classification problem. So if we have k class for example, for the image or for the region proposal, we have to plus one. One is represent for the background. So the result is like this. The number of result is k plus 1. But for bounding box, the number of result is 4 times k plus 1. 4 is because for bounding box we have 4 coordinate x, y, w, h. It's like this. So with these two output, we could get the result. So this is the architecture of fast RCN. Just like RCN, since the dataset, we don't have enough dataset to train a model, so we have to pre-train the architecture. So we use this method to pre-train the network. For example, we create a model like this. With this model, we pre-train the model architecture. We train the model with ImageNet, which have 1000 classes, and the input. Since for ImageNet, the input is one image, and for one image, there's one classes. So we don't have, for example, we don't need to create bounding box, and we don't have the label for bounding box. So we just one label for one image. So we train the model like this. With this is deep convolutional neural network. For the deep convolutional neural network, it's just like this. So this is the same. And then we use max pooling to get this feature map, and then we use two fully connected neural network, and use fully connected neural network plus softmax to get 1000 classes. And And after we train this model with ImageNet, we could turn this, for example, this architecture into the fast RCN. There are 3 steps. The first one is change the mask pooling into ROI pooling layer, which means this layer is dynamic. This is according to the input size. But for the output, this is fixed. First one, we have changed this one by this one. We replace or replace this one by this one. And the second is to, since for the output of fast RCN, there are 2 outputs. So we have to add bounding box regression. Here is just 1. So we have to add this one. And the third is the projection part. Because for the pre-trained neural network, we just have deep convolutional neural network. And for fast RCN, we have to project the bounding box like this. So we have to add this one. So after we change this one, into this one, change the pre-trained model into this one. We have for example, we have the weights for this part and weights for this part, and other for the other parts with other part of the weights, we have to train the model. So here, for our architecture, the loss function is very important. So since the output we have 2 outputs, so normally we have 2 loss function or 2 parts of the loss function. So first we will explain the first part, which means is classification loss. We know that here we have k+1 categories, and then we have the distribution. For example, we have a probability distribution P like this. P0 is represent for the background, and P1, P3, P2 represent for the categories or classes. For example, for we have this one 0.5, 0.1, 0.2, or something like that. For example, which represent the probability of each class. And then we use TK, for example, with the TX, TY, TW, TH, which represent for the bounding box regression. This is just like RCN, and we already explained it in the previous video. If you like to know the detail of this part, you can check the previous video. And then this is the loss function. So for loss function, there are 2 parts. This is classification loss, and we already know this part. And for bounding box regression, first we will explain the U. U represent the ground truth class, which means if U is greater or equal than 1, this means it's the object. So we said it's 1. And if U is 0, which means it's background. For background, we don't need to do bounding box regression. So we should set it to 0. So this is 0, for example. And second, we will explain the lambda. Lambda is used to balance this part and this part. For example, if lambda is 0, this is, for example, this is 0. But if lambda is very high, for example, it's 1000. So which means this part the loss of this part is more important than this part. So normally we set lambda equals to 1 for example, equals to 1 in the training step. And then here we just want to show for example, the activation function or the loss function like this. For example, it's not activation function, it's loss function. Here we use the loss function is smooth L1. We can notice that for the curve is like this. For example, if we have the result error like this with more 2.5, but if we use L1, L2 is used by RCN. For example, RCN, we know that if we use L2, the error the result is very high. For example, if we get a result, it's very high. But if we use L1 smooth loss, the result is we are not influenced by that. So by computing by use, for example, gradient descent method, this we are the result is of this one is better than L2. And finally, we'll explain the SVD method. With this SVD method, the training step could be faster than the result, than which the part without SVD. So first, we will explain why we use this method of SVD. According to the paper, for example, for one image, if we want to get this part, the computation of this time is only one time. So it's normally we don't take much time in this part. But if we want to get a feature map for the region proposal, we have to compute. For example, use this one. This one is for example for one image is 2,000 times. So in total, this part the time takes for this part is far more than this part. So if we for example compress this part and the time of training, the training time could be better, could be speed. We could use less time to train a model. So here is the, for example, this is the SVD decomposition, I think. For example, if we have a matrix like this, U by V, so we can decompose a matrix by U by N and N by N and N by V, and this is the, and for this one lambda 1 normally is greater than this one, so it's the, for example, this one is important in this one and important in this one. So we could use at least this part by this part and by this part to represent the result, to represent the original matrix and the result. Perhaps it's the same or it's almost the same. So which means this one, we could use this part, the matrix, to represent this part. So how could we do that? Here we use if we use this one U by the second layer and this one is first layer, so we could solve the problem. So this is the, for example, this one fully connecting neural network. We have the input X and the weight W, and for this part we get this part, which means W times X, and we decompose this part, these two parts, this part by the two layers. For example, this is X, and this is with this first part we don't have the activation function, and then we use this one and with activation function. So the result is like this, and then we use this, for example, this fully connected neural network to replace this one, and according to the paper, this is faster than the previous one, because for the previous one, the number of the ways is U by V, and after we use that, the number of ways is like this, so it's smaller than the than this part, so it takes less time. Okay, I already explained the neural network. Thank you for watching this video. Thank you very much.